All right, let's get right into it. We're going to be talking about maybe the most successful, and definitely one of the weirdest, theories in all of science. I'm talking about quantum field theory. This is the stuff that really describes the fundamental fabric of our reality. So yeah, let's dive in.
So let me ask you, what do you think the universe is really made of? Deep down. Most of us, we picture these tiny little balls, right? Like little billiard balls, electrons, quarks, that kind of thing. But what if I told you that whole picture is, well, just wrong? What if the universe isn't built from tiny bits of stuff at all, but from something way more mysterious? Something almost like a fluid that's everywhere at once?
Okay, so here's our game plan. First, we're going to explore this whole idea of a universe made of fields. Then, we'll get into how physicists actually draw what's going on when particles interact. After that, we have to tackle the huge problem of infinity that nearly tanked the entire theory. And finally, we'll look at why QFT is both this incredible triumph and still a bit of a mess.
All right, first things first. To even begin to understand this, we have to pretty much throw out everything we think we know about what a particle is. Seriously. This whole idea actually started way back with Michael Faraday, the guy who pictured these invisible lines of force all around magnets. Well, quantum field theory basically takes that idea and runs with it for everything in the universe.
So, what is a quantum field? Okay, try to imagine this. An invisible, kind of fluid-like substance that fills up every single nook and cranny of the universe. And it's not just one big field, oh no. There's an electron field, a quark field, a Higgs field, basically a separate field for every single fundamental particle we've ever discovered. These fields are the real bedrock of reality. This is what it's all made of. And this quote from physicist David Tong just nails it. The things we actually see in our detectors, the electrons, the quarks, the stuff we call matter, they aren't the fundamental thing. They're just ripples, little vibrations, tiny bundles of energy moving through their own specific fields. So an electron isn't some little dot, it's a wave in the electron field. A photon, that's a little ripple in the electromagnetic field. This is a totally different way of looking at the universe.
Okay, so if particles are just ripples, that begs the question, right? What happens when these ripples bump into each other? How do we even describe something like two electrons pushing each other away? Well, to figure that out, physicists came up with a really clever and super powerful visual language.
They're called Feynman diagrams. And honestly, they're basically just little cartoons. The genius Richard Feynman came up with them back in 1948, and they're a kind of graphical shorthand for some ridiculously complicated math. I mean, we're talking about equations that would make your head spin. These diagrams let you see what's happening without getting lost in all of that.
And the rules are actually pretty simple. You've got lines that represent particles moving through space and time. And where those lines meet, that's called a vertex, that's an interaction. That's where the action happens, where one particle might absorb another. But here's the really cool part. Each one of these little drawings isn't just a sketch, it's a precise recipe for a calculation. It tells you exactly what the chances are of that specific interaction actually happening.
So everything's looking great, right? We've got this powerful new theory, these slick diagrams. It feels like we're about to unlock all the secrets of the universe. But then they started trying to calculate more complicated stuff, and that's when they hit a wall. A huge, catastrophic, this makes no sense kind of wall.
The big problem came from diagrams that had loops in them. See, these loops represent something truly weird, virtual particles that just pop into existence out of nowhere, do something, and then vanish a split second later. And when the physicists tried to add up all the possibilities for what these ghostly little particles could be up to, the math just completely fell apart. The answer wasn't just a big number. The answer was infinity.
And think about that for a second. An infinite probability. What does that even mean? It's complete nonsense. It's like saying there's an infinite chance of rain tomorrow. It tells you nothing. For a while, it really looked like the whole theory was just dead in the water. It was predicting gibberish, which is usually a pretty good sign that you've gone horribly, horribly wrong somewhere.
But the solution, when it came, was just a total change in perspective. It was brilliant. Physicists realized that the numbers they were plugging into their equations, the bare mass or bare charge of a particle, weren't the real-world values. The value you actually measure in a lab is different. It's like, think of the bare particle as just you. But the physical particle, the one we see, is you wearing a big, heavy, complicated coat. That coat is the cloud of messy virtual particles buzzing around you. The equations were talking about just you, but the experiments were measuring you plus the coat.
And this whole idea led to a set of mathematical tricks called renormalization. And it's a bit wild, but basically it's a clever way to hide the infinities. You let the infinities from that virtual particle coat get canceled out by the infinities in the bare particle underneath. They just absorb each other. And when the dust settles, you're left with a perfectly finite, sensible answer. And not just any answer, an answer that perfectly matched what we actually measure in the real world.
So, did this all work? I mean, it sounds a little bit like cheating, right? Just canceling out infinities. Well, the answer is a massive, resounding yes. In fact, it didn't just work, it led to some of the most mind-blowingly accurate predictions in the entire history of science.
And the ultimate poster child for this success is a property of the electron called its magnetic moment. Physicists call it G2. Basically, it's a number that tells you how an electron wobbles in a magnetic field. Now, the early theories predicted this number should be exactly 2. Simple, clean, 2. But the new renormalized quantum field theory said, nope, it's going to be a little bit different because of all those crazy virtual particles.
So what happened? Well, after decades of work, we're talking some of the most difficult calculations ever done by humans, paired with some of the most precise experiments ever built, they got the answer. And the number the theory predicted and the number the experiment measured, they matched. And I don't mean they were close. They agreed to something like 12 decimal places. That is just, it's beyond astonishing. It is without a doubt one of the greatest achievements of the human mind, period.
But, and there's always a but in physics, isn't there? Here's the paradox. If this theory is so perfect, if it's the most accurate theory we've ever created, why do so many physicists say it's still incomplete? How can something that works so well be considered flawed?
While the problems are deep down in its foundations. For starters, that whole renormalization trick, the one where you just cancel out infinities, yeah, that makes mathematicians break out in a cold sweat. It works, but it's not what you'd call mathematically clean. And then there's something even weirder. It seems that the standard model, which is our best version of QFT, might just be impossible to simulate on any computer. There's this mathematical theorem that basically says you can't chop up the standard model into little bits or pixels. And since any computer simulation in the world works by chopping things up into pixels, well, you see the problem. It means you literally can't simulate the fundamental laws of our universe. I love this quote from David Tong, who basically says, if you believe this theorem, it's proof we're not living in the Matrix.
And that leaves us with a really deep question to chew on. Does this all mean our universe is fundamentally smooth? Continuous, without any pixels at the bottom. Is that what QFT is telling us? Or is all this weirdness, the hidden infinities, the fact that we can't simulate it, is that just a giant flashing sign pointing the way to an even deeper, more complete theory of everything that we just haven't discovered yet? That right there is the big mystery.